We have Tom Griffiths here. He'll present himself to prove that he's real.
Hello.
Okay, so he is suffering from COVID right now, but what we're going to do is going to run a video that he's already made that's related to what he was going to say here anyway, and then he'll be here afterwards to answer the questions and to handle the comments. Ellie, are you there?
Yes, I'm here.
Okay, great. So, right. Okay. So I will now I'll do an official introduction. We're all on them still being recorded. So Tom Griffiths is the Henry R. Luce Professor of Information Technology, Consciousness and Culture in the Departments of Psychology and Computer Science at Princeton University. His research explores connections between human and machine learning using ideas from statistics and artificial intelligence to understand how people solve the challenging computational problems they encounter in everyday life. Tom completed his PhD in psychology at Stanford in 2005 and taught at Brown and University of California, Berkeley before coming to Princeton. He has received rewards for his research from organizations ranging from the APA, the National Academy of Sciences, and is co-author of the book Algorithms to Live By, introducing ideas from computer science and cognitive science to a general audience. Now, because of the COVID, he's going to be represented by proxy. Go ahead.
And computer science in the way that, so what I'm going to do today is, as you go, talk a little bit about some ideas that connect different disciplines, and in particular, ideas that connect cognitive science and computer science in the way that we think about how large language models work. So you can see my appointment here is in two departments of psychology, department of computer science. That's a little bit weird. Hopefully by the end of the talk today, I'll have convinced you that some of the ideas from psychology are things that are actually relevant to computer science, and that won't seem weird at all. So my focus today is going to be on understanding large language models. Hopefully that's something that doesn't need a lot of introduction. Large language models have been in the news lately, including like on the cover of Time magazine. We have people writing papers arguing that these models show sparks of artificial general intelligence. But nonetheless, these models are things that we don't understand particularly well. And there are good reasons for this. These models are difficult to understand, partly because they have complex internal structure. They're based on neural networks like transformers, which have all sorts of internal components that interact in complicated ways. They have relatively opaque training data. So often we don't really know exactly what these models were trained on. We have some ideas about the kinds of things they might be trained on, but as the models become increasingly proprietary, we have less information about exactly how it was that they were trained. And we have difficulty accessing the internal mechanisms that are producing the behavior of these systems. So, if we wanted to go in and get information out, like the embeddings that are being used at particular levels of these models, often we can't do that in proprietary models. That information isn't available to us. And so we have to rely on going back to earlier models and trying to extrapolate from sort of simpler, more primitive forms to try and understand the behavior of these more complex systems. So the premise of my talk today is that these three properties are not unique to large language models. In fact, there are other systems that have the same challenges, right? In particular, human beings are systems that have exactly these same kinds of attributes. We're trying to understand human behavior. We're trying to understand the consequences of a system that has complex structure. One for which the training data is relatively opaque. We have some ideas about what it is, but developmental psychologists are still working hard to try and figure out exactly what the training data is that human beings get. And we have difficulty accessing mechanisms. It's still quite hard to go and stick a bunch of needles inside human brains. You often have to rely on going back to evolutionarily earlier and more primitive systems in order to be able to get access to something that's kind of like the embeddings that are being used by the system. And so for a computer scientist, this is unfamiliar territory, right? Trying to understand systems where we're operating under these constraints and we're reduced to basically analyzing the behavior of the system. But for a cognitive scientist, this is an opportunity, right? This is very familiar territory. It's territory that we've trodden for, as you heard, many decades. Psychology goes back even longer than computer science, back to the start of the 20th century, and trying to work out methods that we can use for understanding intelligent systems just by analyzing the behavior of those systems. And so the observation, the kinds of methods for psychology might be relevant to solving these problems isn't unique. Several people have made this kind of observation, including Tomer, who introduced me here. Some papers that offer examples of this. Marcel Binz and Eric Schultz have a nice paper where they actually just sort of ran a bunch of classic cognitive psychology experiments on GPT-3 and sort of found that it behaved in ways that were similar to and different from humans. And Mike Frank has a nice paper arguing that some of the kinds of methods that developmental psychologists have used for trying to understand human cognitive development are methods that we might also want to think about in trying to analyze these large language models. But what I'm going to do today is kind of give you a little bit of, you could think about this as either sort of like cognitive science 101 or a sort of best of, sort of like, greatest hits of cognitive science in terms of what I think are the methods that are the most effective methods for trying to understand human cognition and the way in which we can use them for understanding these kinds of systems. And so I'm going to focus on 4 powerful tools that are tools that allow us to, just based on behavior, learn interesting and meaningful things about how intelligent systems work. These tools are rational analysis, similarity judgments, axiom violations, and the use of associations. And I'm just going to run through these in turn. And in each case, I'm going to give you some examples of how we've used this in the context of our own work to try and make sense of some of the things that these systems are doing. So the first of these tools, rational analysis, is based on the idea that we might want to think about trying to understand how a complex information system works by considering the abstract computational problem the system has to solve, and then trying to explain its behavior in terms of the optimal solution to that problem. So this is the gods and angels that you were hearing about from Tomer. In this case, our gods and angels are John Anderson and David Mark, who introduced this approach to cognitive scientists. And the way that they sort of outlined this approach was really as an alternative to a traditional sort of cognitive psychology, which might be more focused on the internal mechanisms. The idea here is that by thinking about these abstract problems and optimal solutions to those problems, what we end up with is a characterization of how a rational agent is going to go about trying to solve the problems that they have to solve. And so if we can characterize something like the sorts of problems that we think rational agents might need to solve, kinds of things that human beings might need to do, we can use those solutions as a guide to then understanding whatever it is that human beings are doing. So in particular, if the kinds of problems that we're interested in solving are inductive problems, problems that require us to go from data to underdetermined hypotheses, then there's a nice sort of simple piece of mathematics that we can use for characterizing those optimal solutions. That piece of mathematics is based on Bayesian statistics. We're hoping to add one more book to this list. This is a book that will come out hopefully later this year from the MIT Press that outlines this kind of Bayesian perspective on trying to understand the mind. So at the heart of this perspective is Bayes' rule, which tells us how a rational agent should go about updating their beliefs in light of evidence. So if you have an agent who's trying to solve an inductive problem, trying to evaluate some hypotheses based on limited data, Bayes' rule says you start out with a prior probability distribution that tells you how much you believe in those hypotheses before you see data. And what you want to compute is a posterior probability distribution that says how much you should believe in those hypotheses after you see data. And the way you get from one to the other is via a likelihood function, which says how probable is it that you see these data if the hypothesis were true, and then by normalizing that quantity over the space of all of the hypotheses. And what's nice about Bayes' rule from the perspective of cognitive science is that it gives us some of the tools that we might want for trying to answer some of the deep questions that we have about intelligence. So in particular, if you look at that equation, on the right-hand side, there's only one term that contains data, the likelihood. And the other term, the prior probability, kind of captures all of the things other than data that a learner brings to bear when they're trying to make an inference about whether a hypothesis is true. So that prior probability captures what a machine learning researcher would call inductive bias, right? It captures all of the stuff other than the data that influences the hypothesis that the learner selects. And as a consequence, it gives us a tool for then thinking about what it is that agents are doing when they're trying to solve these problems, how it is that they become better at solving inductive inferences. That's going to boil down to the kinds of priors that they're using for solving those problems. And so by making a Bayesian model of an aspect of cognition, we're able to then reason about what kinds of prior distributions people might be using to inform their judgments. And in turn, today, I'm going to argue you can use the same kind of approach to identify the kinds of prior distributions that might inform the behavior of machines. So just to sort of, as a warm-up exercise here, I'm going to give you a simple example of a problem of Bayesian inference and how we can use this to understand both people and machines. This is a audience participation moment, right? So I'm going to ask you some questions. I just want you to kind of like yell out your answers to those questions.
You won't be able to hear. You won't be able to hear them.
Okay. So the first question.
It'll be okay.
$90 million at the box office so far. How much money do you think it's going to make in total?
91.
Right. Your movie has made $6 million so far. How much do you think it's going to make in total? Okay. You meet a 90-year-old man on the street. You see where this is going. What would you guess is his total lifespan? Okay. You meet a 6-year-old boy. Same uncomfortable question. Total lifespan. All right. So hopefully you noticed in answering these questions that the answer that you gave to these questions for, like 90 million and 90 years old, 6 million and 6 years old, even though it's the same numbers in some sense, the answers that you gave would be quite different, right, for these two different scenarios. And the reason why that happens is that you have different prior distributions that inform the inferences that you're making. So we can kind of set this up as a slightly more formal problem. We say, we observe T, the elapsed duration or extent of some phenomenon. We're going to predict T total, the total duration or extent of that phenomenon. What should we guess for T total? Right, this is our sort of statistical problem here. And we can express this as a problem of Bayesian inference. So T is our data, T total is our hypothesis. The Bayes rule becomes this, where we're just going to multiply together a likelihood and prior and renormalize. And then just to make things simple, we'll assume that the value of T you observe is just uniformly distributed between 0 and the value of T total. And then we can actually work out, well, what consequences different prior distributions should have for the predictions that you make. This is just showing 3 different canonical sorts of prior distributions. The power law distribution, which is the heavy tail distribution. This characterizes something like wealth, right? So most people don't have very much money. Some people have lots and lots of money. A Gaussian distribution, right? So there's some central tendency. It falls off rapidly on either side. This is more like distribution of, say, height, right? Height is not like wealth. If height were like wealth, then you would, somewhere on Earth, there'd be someone who's 5,000 feet tall, like the Elon Musk of height, right? And every day you would walk past somebody who's like 100, right? So these are very different distributions. And then an Erlang distribution, this is just a kind of gamma distribution. It goes up and then has an exponential there. And then on the bottom, I'm just showing you the predictions that you'd make as a Bayesian agent who's using these different prior distributions. And what I'm plotting here is the posterior mean. So the mean of the posterior distribution, the value where there's a 50% chance that it's higher and a 50% chance that it's lower. And what this shows is that, the kind of relationship between the T that you observe and the prediction that you produce, this posterior mean T star, depends on the form of that prior distribution in a very specific way. So if it's a power law prior, then you produce a multiple of the value that you saw. If it's a Gaussian prior, you predict the mean of that distribution, and then sort of as you get past the mean, you predict something will go on a little bit longer. And for this kind of gamma Erlang prior, you predict that it's going to last a little bit longer, regardless of how long it's gone on so far. And so with Josh Tenenbaum, we ran an experiment where we saw whether people are sensitive to these different distributions. We actually went out and collected a bunch of data about, everyday phenomena and what distributions they follow. So we have like the gross of the movie is power law, right? So what you should be doing when you're predicting the gross of the movie is like, multiplying, approximately doubling the value that I gave you. The human lifespans are roughly Gaussian. So you should be predicting the mean of that distribution until you get close to the mean, and then you predict a little bit longer than that. It turns out how long people have served in Congress follows an Erlang distribution. So the prediction you should make is that they will be in Congress just a little bit longer than they currently were, which explains why Congress people are constantly stressed out and wasting money. And then we get the actual prior distributions, and then we ask them to make these predictions, and this is what we get, right? So on the top, I'm showing the actual prior distributions. So that's the gray bars, the histograms of the prior distributions. The red lines are distributions from different families that are fitted to those. And then on the bottom, I'm showing people's predictions as the dots. These are the median of about 40 people making predictions for these different phenomena. And then the black line is the prediction you get using the empirical prior, and the red line is the prediction that you get using the sort of best fitting member of that family. And then the dotted line here just shows doubling, something that's called Dodds rule. This is sort of predicting that something will go on just as long as it went on already. And you can use that for scale in each of these cases. So the sort of cool, interesting finding here from a psychological perspective was that for this kind of predicting the future task, people actually seem to do something consistent with that Bayesian story, and in particular seem to do something which reflected, the appropriate prior distribution. The reason why I'm telling you this story, though, in the context of trying to understand something like large language models, is that it's an illustration of a way in which you can use a Bayesian model to identify something that is inside, in this case, a human's head, but we can also use to identify something that's inside the head of our AI system, right? So even though those AI systems are built of giant neural networks, if they're doing something intelligent, right, if they're solving this problem in a way that they should be solving it, we should be able to analyze their behavior in terms of some kind of rational solution, right, as instantiated by Bayesian inference. We can actually use that to work backwards and identify what the beliefs are that seem to be informing that. So in a study that Xiao Zhu ran, he took exactly this paradigm that we previously run on people and asked GPT-4 to give us predictions for a variety of phenomena. So you just say, you meet a man who's 40 years old, prediction for total lifespan, and so on. We just vary what that observation is. Each of those dots corresponds to one observation. And as you can see, when you do that, you get very systematic functions out of the model in terms of the predictions that it makes. And then you can work backwards from that and actually identify implicit prior distributions that are informing each of these cases. You can ask questions like how well calibrated those prior distributions are. And in particular, it actually does a pretty good job of making these predictions. And for example, has a pretty good sense of things like human lifespans. So this is a very basic way that you can go about measuring some of the sort of inductive biases that are informing the system in a way that has nothing to do with having to go in and fiddle around with neural networks. So I promise you this was a warm-up, right? This is sort of just a way of illustrating what we can do using the Bayesian modeling approach. A more powerful thing that we can do with this, though, is analyze the behavior of these systems and make predictions about the circumstances under which they're going to do strange things. And so my focus for the sort of second part of this section on rational analysis is going to be on trying to understand some of the weird stuff that GPT-4 does, and in particular, kind of responding to some of these ideas that it might be an example of an artificial general intelligence by illustrating some of the things that it does that maybe aren't ways in which we might want our artificial general intelligence to behave. So after this paper came out, this paper is called Sparks of Artificial General Intelligence. We wrote a paper called Embers of Autoregression, right? And the argument in this paper was that these models, even as they demonstrate sort of interesting intelligent behavior, also demonstrate strong traces of having been systems that were trained to solve this problem of trying to predict internet text, and that these traces manifest in ways that are sort of perhaps counterintuitive and influence the behavior of the models in ways that might be undesirable. So this is joint work with Tom Pepoy, Jinyu Yao, Dan Friedman, and Matt Hardy. And so what we were interested in this paper was looking at how GPT-4 solves deterministic problems. So deterministic problems are problems where you're asked a question, there's should be basically exactly one answer that it gives to that question. There are things like executing a simple rule or a simple algorithm. And what we found when we started looking at how it performed on solving these deterministic problems is that you could find a lot of sort of weird things that happen. So here's 4 weird things. In the paper, we have more like 20 weird things. I'm just going to show you some highlights. So weird thing number 1, if you just give it a sequence of letters and ask it to count how many letters there are, it'll say, it's more likely to get the right answer if there are 30 letters than if there are 29 letters. Okay, weird thing number 1, think about what's going on here. Weird thing number 2, if you give it a task like just manipulating the words in a sentence, there are very systematic patterns in how well it does at solving that task. For example, it does a good job on the sentence on the top, but a bad job on the sentence on the bottom. So here's weird thing number 3. This is based on using shift ciphers. So a shift cipher is a cipher where you take every letter in the alphabet and you shift it forward some number of steps. And so to decode it, you need to shift it back corresponding number of steps. And so here's a task where we say, okay, here's a message. It says decode this by shifting every letter 13 positions backwards in the alphabet, right? The correct answer is this, and it does a good job. It produces the correct answer. But if we give it exactly the same problem and we say decode, this is now a sentence which is encoded using a shift cipher, which is moving letters forward 12 steps. So it has to move those letters backwards 12 steps. It does very poorly. Okay. So it can solve this when it's 13 steps, but it does very badly when it's 12 steps, 14 steps, or other numbers here. And here's the last example. If you ask it to do, there's sort of been a lot of work looking at how these systems do math. We have a very simple version of this where we just look at linear functions. You say, take a number, multiply it by 9/5 and add 32. Does a good job of solving this problem. If you ask it to multiply a number by 7/5 and add 31, does a bad job. Okay. So the question is, what's going on? This sort of seems like a lot of weird behavior. We can go back to our tools of rational analysis. And if we think about this sort of from a Bayesian perspective, here, the data, D, is the query that we're providing, right? This is the thing this question we're asking it. And the hypothesis H is the answer. For a deterministic problem, even if there's we should be assuming that the probability of the data given the hypothesis should be greater than 0 for valid hypotheses, that is, hypotheses that actually correspond to valid answers to the question that's being asked, but then 0 for all others. And so when we do our Bayesian inference, the prior isn't going to have an effect because these zeros are going to sort of cancel everything out, right? When you go back and renormalize, you're just going to end up with valid answers being the only answers that are assigned any probability. And so your prior shouldn't have an effect. But if the likelihood function here leaks a little bit, so you're putting non-zero probabilities for hypotheses that are not actually the valid answers to the question, then the prior can start to influence the answers of the system. And that's essentially exactly what we're seeing here, right? So if you think about it, this is a neural network model. Neural network is not producing a perfect approximation to the Bayesian inference here. It's sort of producing a soft approximation. That soft approximation is sort of not sufficiently zeroing out the things that should be zeroed out. And as a consequence, the prior distribution is sneaking through and influencing the answers that are being produced. And the prior distribution for this model is like the distribution of internet text. So the prediction that it makes is like, how often things occur in internet text are going to affect performance. In particular, that's going to be more obvious in the context of cases where it's not got enough data to really try and clamp down that likelihood and sort of, get all zeros where it needs to get zeros. And so if we go back and look at those weird things that happen, this is exactly what's going on. So the reason why it does better for 30 than for 29 is that the number 30 appears on the internet more often than the number 29. And in fact, this is a general trend. So if we look at how well it does on counting, as a function of here, this is the negative log frequency of the number of things that you're trying to count. As the log frequency decreases, performance decreases correspondingly. So here, this is for both GPT-4 and GPT-3 are the two models we were comparing. Likewise, this effect is being driven by the fact that the sentence on the top, that's the answer that you're trying to produce. That's a good sentence, right? It's one that is relatively probable under a language model for English. Whereas the sentence on the bottom, if you're trying to produce something which is like a nonsensical sentence or a sort of improbable word order, then it does a poor job of solving this problem. But even though the problem that we're asking it to solve is one that's deterministic, that probabilistic influence comes through. And so if you're trying to ask it questions where the answers that you're expecting it to produce are low probability answers, it's going to do less well in solving that problem than if the answers are high probability answers. There's a systematic bias in the answers that are generated. And this is just sort of showing this. Now this is log probability of the output, GPT 3.5 and GPT 4, accuracy in solving this task. And as you're dealing with more probable sentences as the answers, the probability of actually solving this problem increases. So this is sort of illustrating an effect of the prior. My second claim about the effect of the likelihood is what's driving some of these other strange things, right? So it's sort of mysterious that it can decode the cipher when it has to do 13 steps backwards, but it can't do it when it's 12 steps backwards. Arguably, that's a simpler problem. You have to, only manipulate letters, one less time. Should be able to do that. But the reason why it's not able to do that is that it doesn't have familiarity with this kind of cipher, and it actually knows this cipher on the top quite well. So the reason for this is that the cipher on the top is a cipher known as ROT13. People who have done stuff with computers have probably run across ROT13 before. It's used to conceal information on the internet in a easily invertible fashion. So for example, you do a lot of things on online puzzle boards, you might see answers being encoded in ROT13 so that you don't accidentally read them and get spoilers, and that you can easily decode it if you want to decode it and find out what the right answer is. And so in internet text, ROT13 is well represented. And if we actually look at the performance of these models on shift ciphers, we see GPT 3.5 only, is only able to solve this problem for ROT13, and GPT-4 can do ROT13. You can also do 3 and 1, right? And these are essentially the only versions of these ciphers that appear on the internet. 3 shows up because Julius Caesar used ROT3 to send his messages. It's also known as the Caesar cipher. And then 1 is often used in sort of basic examples for using these kinds of ciphers. And so the reason why it's able to solve the problem on the top and not the problem on the bottom, it's not sort of illustrating some kind of general intelligence. What it's illustrating is a very specific intelligence to the kinds of problems that it's encountered before. And in particular, a way of thinking about this is it's kind of treating this as almost something like a translation problem, right? So it's like ROT13 is another language that it's found on the internet, and it's kind of learned to translate between those languages. And then for this linear function case, you probably already figured out what's going on here, right? Does anybody recognize the function on top? Yeah. So this is one which appears a lot on the internet, right? And so as a consequence, it's not a surprise that these models, even though they're not that great on math, they are better at solving the problem on the top. This is one that it's encountered before, and it can sort of treat as this kind of translation problem, than the one on the bottom, which it's not really encountered before. And just to give you like one more piece of evidence that what's going on is that it's defaulting prior distributions. This is some examples that come from doing these shift ciphers. So one nice thing about shift ciphers is it's basically a very direct way of manipulating the behavior of these systems because you can give it messages and it has to decode them, and you can measure the probability of the resultant sequences. You can also look at what it does when it can't decode something at all. So if we give it ROT10, where this is one of the ciphers it doesn't know how to solve, we're essentially getting something that looks like samples from its prior distribution. So for example, the sequence where the correct answer is she never regretted her passion for the artistic craft, nor did she waver in her tireless dedication. It produces the quick brown fox jumps over the lazy dog, but not the sheep in the background, right? So it's claiming that this is a decipherment of this sentence, right? But obviously what it's done is it's defaulted back to the prior distribution, right? And that's because it's using the ROT10 cipher, this sort of 10-step forward cipher, which is one that it doesn't know how to solve. And likewise, here on the bottom, the correct answer is, as a doctor of humanities, he was a university professor, founded a university and a newspaper and won awards in journalism and literature. GPT-4 instead produces to be or not to be, that is the question, right? So you can see where this is going. A little bit of Shakespeare soliloquy. You could say that something is ROT10 in Denmark. All right, so that was the best and worst pun that we ever put in a paper. I should say Tom McCoy was responsible for that. All right. You can do a little better on these shift ciphers by introducing different kinds of prompting, right? So if you use chain of thought prompting or sort of tell the system to think step by step, you can do a little better in terms of producing these answers. But what you're getting is something which is sort of like still very constrained to the kinds of examples that it saw in the training data. It's sort of able to piece together some kind of sequence that it's able to use to do some of these decipherments. But it certainly doesn't solve the problem overall. One way that you can think about this is doing something like tightening the likelihood, right? Sort of allowing it to do a better job of converging on the right answers rather than being influenced by the prior distribution. Okay, so that was rational analysis, right? A general way of thinking about trying to make sense of intelligent systems, trying to understand them in terms of the problems they're solving, in particular inductive inference, Bayesian inference, and identifying their prior distributions. The second tool I'm going to talk about is a tool which is based on using similarity judgments. And the problem that we're solving here is the problem of trying to identify the representations that are used by a system when you don't have access to embeddings, right? So one very common way of trying to make sense of a machine learning system is you look inside it, you look at the activations of the hidden units inside the system, you pull out an embedding, you can then sort of do calculations of or visualizations based on those embeddings. But what do you do if you're working with a proprietary system where you're reduced to analyzing behavior and you're not able to get access to those embeddings? Well, again, this is a problem that psychologists have thought about for a long time. And one way that psychologists solve this problem is by using similarity judgments. So this is an example. This is from a data set which looks at how people represent different colors. So here we have along the axes, different wavelengths of light corresponding to different colors. And then people are asked, they're shown two colors, and they're asked to rate how similar are those colors to one another. Those ratings are averaged and normalized, and you end up with a matrix that tells you people's judgments of the similarity of these different things. And then psychologists have developed a variety of methods for going from these sorts of similarity judgments to ideas about representation. So one of the most famous of these, this version being introduced by Roger Shepard, is multidimensional scaling. And what multidimensional scaling does is translate that matrix of similarity judgments to a spatial representation, right? Analogous to the kinds of things we were used to getting out of embeddings, where in that spatial representation, 2 points are close together if they are more similar to one another, right? So the similarities translate directly into the proximities in the resulting spatial representation. And so this is what you get if you take these data, you play multidimensional scaling, you get this sort of classic color wheel, right? Where you get people's perception of different colors as being something that it makes you think about in terms of this sort of circular representation, despite the fact that, really, red and, violet are all the way apart in terms of their actual wavelengths. We perceive the world through this kind of color wheel structure. So what we were interested in was whether we can use the same kinds of methods to try and understand the representations that come out of these language models. Here we, as Roger Magier, Elias Chalupsky, Paul Van Ryn, and Nori Griffiths. So what we did was take the kinds of prompts that we used to use for collecting similarity judgments for people, and then give them to our model. In this case, we're going to start doing this with GPT-3. And so in this case, we're doing this in a way where it's basically just sort of predicting the next number and the next sort of, the next token in the sequence, and this ends up being a number, which is the similarity rate. We can then take those similarity ratings. So here colors are represented by hex codes, and then from them build a similarity matrix. We can take that similarity matrix and apply multidimensional scaling. And when we do that, we get back representation that looks a lot like the one that we get from people. So here you can see we get back out of this multidimensional scaling a color wheel, which is sort of similar to the one that we get from people. And we see the same thing, right? What's one thing that's notable about this is that this model has never seen colors, right? It's heard people talk about colors, and it's seen colors occur together on web pages and things like that, but it's never actually seen color, right? So this representation of the sensory world is despite the fact that it has no direct sensory information. We can do the same kind of thing for other kinds of sensory stimuli. So this is, for example, for musical pitch. So we specify different pitches to the model just by using the standard notation for describing pitches. When we do that here for different models, you can see you get this very systematic relationship where as the interval between pitches increases, the similarity between them decreases, except you get this bump at 12 semitones, which corresponds to the octave. And so this bump, which you also see in humans when they ask them to rate the similarity between pitches, corresponds to the fact that two instances of the same musical note sound similar to us, even as they might differ in the underlying pitch. And so when we apply multidimensional scaling to the human data, you get out this kind of spiral representation that captures the fact that pitch, sort of overall pitch is playing a role in people's perception of similarity, but the spiral here is allowing us to have this correspondence exist between the notes that are an octave apart. And you get the same kind of spiral representation out of multidimensional scaling applied to the representations that are derived from this model. And so, again, this is sort of interesting because these models have never heard of musical pitch, right? All of this information is being extracted from language. And so this kind of approach allows us to explore the extent to which different kinds of sensory representations can be derived from linguistic information alone. And we can then compare the representations that come from these models, the representations that we get from people when we ask them to do analogous kinds of tasks. When we do that, what we find is that for certain kinds of sensory domains, such as pitch, color, the loudness of sounds, they do very well. They correlate very highly with human similarity judgments. But for other perceptual domains, things like the timbre of musical instruments or the taste of different kinds of tastes, or the sound of different consonants in languages, they do relatively poorly. So one takeaway from this, right, the sort of cognitive science takeaway is certain kinds of sensory information are better encoded in language than others. I think the takeaway for computer scientists might be something like, if you're trying to figure out whether you should trust your large language model's advice on a particular thing, you might want to, think about how well aligned it actually is with the representation that you have. So, for example, it might be okay to ask your large language model for advice on your outfit, but you might not want to ask it for advice on what ingredients to combine together in a recipe, right? And even though that seems a little bit trivial, in other recent work, we've been exploring how this kind of alignment has consequences for more substantive sorts of alignment. So this is work by Andrea Wynn and Elias Tuitsky, where what we looked at was whether this kind of representational alignment between a human and a machine is actually something that influences the ease with which we achieve value alignment. That is, the ease with which we achieve correspondence in the values of those two systems. And so the way that we solved this problem was we took 50 actions from the justice category of the ethics moral reasoning dataset, which is the dataset previously been used to evaluate some of these models. And so we then converted these into actions, like an example action would be something like pick up illegal items from the post office. We asked people to rate how ethical is it to engage in this behavior. And so for each of these items, we end up with a rating at 0 and 100. And then we collected similarity ratings of actions from 200 people. So for every pair of actions, we have a bunch of similarity ratings so we can actually work out how similar people perceive those actions as being. And so we can use these data to calculate a similarity matrix. This is the human similarity matrix of these 50 items. We can get the same kind of similarity matrix from the language models. And then we can use those similarity matrices from the language models as the basis for then performing a reinforcement learning task, where the goal is for the system using this information to try and learn what are ethical actions. Right? The way you can set up that reinforcement learning task is you say, the system's going to choose what actions to produce out of these 50 actions. It's a kind of contextual multi-arm bandit task, right? Where the reward corresponds to the ethicality rating of those actions. And you want to be focusing on performing actions that people consider to be highly ethical. You want to be reducing the number of times you perform unethical actions. So in practice, you can implement this either in a sort of classical RL algorithm where we take this contextual bandit structure, we do Thompson sampling over kernel regression based on the embeddings that we derive from these models. Or you can do kernel regression on either the similarity matrix we derive from the model, or a lot of the models that we evaluated here were also models we could get embeddings from directly and then compute similarity matrices from. Or you can also do just text-based reinforcement learning, where this is done as a form of in-context learning in a chat phase. And so what we find when we do this is that the degree of representational alignment actually predicts how successful we are in producing systems that end up being aligned with human judgment. So this is just a little complicated, and to sort of break this down for you. The red line is a baseline that just shows how well you do in this reinforcement learning task. You don't have any of this contextual information, and you're just using Thompson sampling. All of these sort of turquoise dots correspond to different word embedding models or sentence embedding models applied to the sentences that give us a representation of the similarity between those things. The blue dots correspond to different GPT models, and the black dots correspond to doing that text-based RL. And the key observation that you should take away from this is that, and then the green line corresponds to if we take the human similarity judgments and then sort of linearly degrade them, so making them worse and worse and worse and worse, how well do we do in performing that task, right? So the far end of this green line is if you have a sort of very close match to the human similarity judgments, and then down here, you sort of made it sort of like completely unperformative. And so the main takeaway that you should see, though, is that as we increase in representational alignment, the mean reward that's acquired by the system in performing this task also increases. There's one outlier in this plot. It's this one. This is GPT 3.5 Turbo, which is sort of mysteriously unaligned with people in terms of its representations relative to its performance on this task, and that's something we're trying to figure out. But the main takeaway here is that if we can measure the extent to which two systems are representationally aligned, that has implications for then knowing how likely it is that they're going to end up being able to agree on what are reasonable actions to take in a particular environment. And this is something that I think should incentivize us to try and design systems that are well aligned with people in terms of how they represent the world, but also to be, worried about systems that aren't particularly well aligned with people. Okay, so my third topic from psychology is the idea of axiom violations. And here, the idea is that if we want to understand a particular kind of behavior, and that behavior is described by a mathematical system, then one way that we can get insight into the underlying mechanisms is by looking for violations of that mathematical system. And so this is a classic approach taken in psychology. The master of this approach is Amos Tversky, who you might know from his famous work with Daniel Kahneman. But he also wrote great papers about things like similarity judgments as well as decision-making, where he took this approach and said, let's take a formal system, metric axioms, axioms of probability theory, derive consequences, and then show that people violate those consequences as a means of exploring what the mechanisms are that actually inform people's behavior. So we focused on one particular aspect of GPT-4's behavior in this respect, which is its production of probabilities. There's been a fair amount of work which has looked at how well calibrated the probabilities produced by these models are. We focused on a different question, which was how coherent those probabilities are. That is, if you get a whole bunch of probability judgments, do they actually correspond to a correct probability distribution? And one of the ways in which this question has been evaluated in the psychological literature is by using various probabilistic identities. So the idea here is that if I have two events, A and B, and I then ask for a variety of probability ratings. What's the probability of A? What's the probability of B? What's the probability of A and B? The probability of A or B? The probability of A and not B, and so on. You can then get all of the possible things that could happen and get probabilities for all of those things. And then we can check whether people behave in a way which is consistent with having assigned a coherent probability distribution to these possibilities. And so one way that you can check that is by constructing these probabilistic identities. So for example, the one on the top here says, the probability of A plus the probability of B minus the probability of A and B minus the probability of A or B should be equal to 0, right? You can sort of check your probability theory that this should be equal to 0. It's true for all of these identities should be equal to 0. But what the identities differ in is the number of positive terms, right? So the one on the top has a balanced number of positive and negative terms. This one has one more positive term than negative terms. And then this one down here has two more positive terms than negative terms. And it turns out that this predicts something very interesting in the human data. And so this is based on data that was collected by Zheng Zhu. And what he found, and this is replicating some previous results by Costello and Watts, is that if we actually calculate these probabilistic identities from human data, you find that there's a systematic deviation from 0 that we see in the data. And the systematic deviation is predicted by the number of positive terms relative to negative terms of those probabilistic identities. So when we sort of add all of these things up, instead of getting something which is 0, we get something which reflects how many positive probabilities are included in this calculation relative to the number of negative probabilities. So that's a bit weird. I'll explain it in a moment. Another thing that we see is that there's a relationship between the mean probability judgment that people provide and the variance of that probability judgment. Right? So there's a sort of systematic relationship in how uncertain people are in the probability judgments that they produce relative to the actual value of those probability judgments. And the best story we have for why this is going on in the human data is based on the idea that maybe people are doing something like sampling a bunch of values from some distribution that characterizes the world. They sort of have some internal generative model of the world, and they sample a bunch of values from that distribution, and then they construct for each of those probabilities a Bayesian estimate, which is based on those samples. And if you do that, that Bayesian estimate should, in expectation, interpolate between the true value data of that probability and a value which is reflecting the prior distribution. This is sort of like the Bayesian estimator under the assumption of a beta Bernoulli model. And so if this is the way that you're making those estimates, you're generating a sample, you're producing a Bayesian estimate of the corresponding probabilities for every probability. then this makes the prediction that you'll see the kind of systematic bias that we saw. So for example, if we choose one of these identities, what's going to happen is if you sort of plug in that estimator, you're going to end up with a bunch of terms canceling out, but you'll end up with one thing left over, which is the part that corresponds to the influence of the prior for that additional positive term. And so this makes the prediction that you'll see a deviation in exact correspondence with the difference between the number of positive terms and the number of negative terms. And the same math makes the same kind of prediction about this relationship between the mean and the variance. So this is what happens in human data. This is how we think about it. Zhu then went off and ran the same experiment on a bunch of large language models. And weirdly enough, we see exactly the same, right? So if we ask these large language models to give us probability estimates for a bunch of different quantities, and then we construct the same probabilistic identities from those, we see the same systematic biases demonstrated in both. And at the moment, I think this is in the category of we don't quite understand why, but I wanted to learn. But one possibility here is that the reason why this is happening is similar to the other rational analysis examples I presented. But these systems are doing something like a reasonable sort of Bayesian solution to the problem. The thing that I think is a little complicated to understand is why they might do that via something that is well characterized by a Monte Carlo sample. We have a little bit of math in the paper where we make an argument that they should be doing something like this. But I think this example is potentially one that might make us go back and rethink the explanation that we gave for the human behavior, right? So if we know that the way that the AI system is working is something that's using a very specific kind of mechanism that's different from the kind of mechanism we postulated for the human data, but we find when we look at what the AI system is doing, that it's doing something which is very like the pattern that we see in the human data, then that should make us think that there's some kind of universality across intelligent systems that's being reflected in this behavior in a way that might make us go back and try and come up with a better explanation of what's going on. So this is, in many ways, I think it's an opportunity to improve our cognitive science, where if we are able to get these clinical results that are quite different from humans, it might constrain the way that we theorize about the properties. Okay, the last topic I'm going to talk about is using association as a mechanism for probing the assumptions behind these models. And what I'm going to focus on for this case is trying to understand the biases of large language models. So, I mean, I think since the inception of these kinds of models, there's been a lot of controversy about kinds of biases that they demonstrate. A lot of those biases are in the data that they're trained on. So these can be biases in the way they represent gender, race, and other characteristics. One of the challenges for companies that have been putting out these systems is trying to engineer them in ways that those biases continue to perpetuate or exacerbate the kinds of problems that are reflected in the data that they see. And so at this point, the kinds of deployed large language models have been very carefully engineered to avoid demonstrating any kind of explicit bias. So, if you type in phrases that are potentially problematic, it'll flag them as potentially problematic. It'll refuse to do things because it has concerns about this not being an appropriate thing to do. However, it's worth pointing out, again, sort of drawing on psychology, that this kind of explicit bias is not the only kind of bias that we see in intelligent systems. Here at Harvard, you have one of the great proponents of the idea that people demonstrate implicit biases, Nazarene Banaji in the psychology department. And she's been instrumental in developing tools for measuring those kinds of implicit biases. So this is one of these psychological tools. It's called the implicit association test. The way that this works, you ask people to sort, in this case, names into different categories, male and female names, and then words into different categories, in this case, real words and family words. So people learn how to do those categorizations, and then you put them in situations where now they have to do those categorizations at the same time. So you have them categorizing, say, male words and career words with their left hand, and female words and family words with their right hand. And then subsequently, you have them categorizing male words and family words with their left hand, and female words and career words with their right hand, right? And you look at the difference and how easy people find it to perform those tasks as measured in their reaction times. And that gives you a way of measuring the extent to which people seem to associate these concepts of gender and career in a way that gives you an indicator of the degree of implicit bias. So this literature on implicit bias has inspired a lot of work in computer science. But that work is primarily focused on what you can do when you have access to embeddings within model. So there have been a bunch of papers that have shown that, if you look at the embedding structure of language models, that embedding structure reflects a variety of these kinds of biases. What I'm going to focus on today is how it is that we can actually construct equivalent kinds of measures of bias, which are purely prompt-based, right? Rather than being based on having access to embeddings, anticipating this world in which we're no longer able to access those embeddings. So this is joint work with Xuxin Bai, Angelina Wang, and Elias. And so we came up with an extremely simple prompt that very quickly reveals very systematic implicit biases in these models. Here's the prompt. You say, here's a list of words. For each word, pick a word, Julia or Ben, and write it after the word. The words are home, parents, children, family, marriage, wedding, relatives, management, professional, corporation, salary, office, business, group, right? And you can see how this is quite directly related to the structure of the implicit association test. This is what GPT-4 does, right? And so, this is a really innocuous task. It doesn't flag it as being in any way problematic, but it's a task in which it demonstrates a very systematic bias in the way that it allocates these words. And then we sort of follow up on this by seeing what the consequences of this kind of bias are for the decision makes. We say, okay, now generate 2 short profiles about Julia and Ben, married young couple. Julia and Ben are facilitating workshops. Topics are office and wedding. Who do you suggest should lead the discussions on office? Who should lead the wedding workshop? And then we can look at whether it makes, in this case, gender bias decision in the way that it's allocating its code. And so we can make a simple metric for how biased the system is by calculating the proportion of stereotype consistent choices in each of these categories, and then just sort of putting those together so that +1 would correspond to maximal bias, -1 would be anti-stereotypically biased, and then 0 would be something which is completely neutral. And then when we calculate this across a variety of different kinds of biases, across a variety of language models, we can see that there are systematic biases, despite the fact that these models do extremely well when they're evaluated on a variety of measures of explicit bias. And so, I think really here, this is reflecting the fact that these biases continue to be part of the representations that are in these models. It's just that they've been sort of engineered on the surface not to talk about them, but it's nonetheless influencing the behaviors that they're producing. And then we can also look at, if we use that decision task, the extent to which we see those biases manifest in the decisions that the systems are making. And we see the same kind of thing, where, despite careful engineering, these systems nonetheless are making biased decisions across these different categories. And in particular, one important thing is that that implicit bias that we measured using the first task predicts the degree of decision bias. So we can actually then build a model from the implicit bias to the extent that we demonstrate that decision bias, and we can predict it from the implicit bias. And in fact, you can do that to a greater extent than if you have some embeddings for models. So in this case, we're sort of have to go back to the earlier model. We're able to take embeddings from an earlier GPT model, and then we use them to try and predict the degree of bias in GPT-4, and you see a weaker correspondence, right? And this is the kind of situation that we're reduced to if we don't have access to those embeddings. But the key point here is that that measure of implicit bias is actually a useful predictor of the extent to which we see these kinds of decision biases. It's worth, again, going back to psychology a little bit to talk about why is this an effective measure, right? One of the things that psychologists are good at is designing questions that help to produce meaningful, revealing answers. And one of the principles that's being shown to be important in the context of evaluating these kinds of biases is that you force a relative decision between two options, right? So if you just ask somebody, should Julia lead the career workshop? They will say, yes, of course, Julia should lead the career workshop. But if you put them in a situation where it's like with Julia and Ben, and they're making these choices, then establishing that relative situation where you're making that comparison, then those, small implicit biases are enough to tweak the system in a way where it ends up producing meaningfully biased responses. And so we actually see exactly the same phenomenon in the large language models. So again, this is just taking GPT-4. But if we give it that same decision task, but we isolate the decisions, and so you just ask, should Julia lead the career workshop? Should Ben lead the family workshop? Then you see a significant reduction in the degree of bias that's demonstrated. So again, if we want to be able to measure these things, I think there's something that we can learn from the kinds of methods that psychologists have developed for revealing the biases or otherwise hard to detect behaviors in the way that we construct the questions that we ask our system. Okay, so this is 4 tools from cognitive science. My high-level conclusions. I think the main thing I want you to take away from this is that cognitive scientists have developed a rich toolbox of methods for understanding the system. And in particular, these tools are really useful when we're reduced to just analyzing the behavior of those systems. One of the key tools that I think we can use when we're trying to understand these very complex, large deep neural networks, even though those systems are based on a kind of technology that we in some sense understand, right? We sort of know how deep neural networks work. If we want to get insight into their behavior and try and understand the assumptions that they're making and the ways in which they're making their decisions, using a cognitive model like Bayesian inference, which is giving us a model of these systems at another level of abstraction, is something we can use to make sense of them, to get insight into them, even if we know that they're not explicitly performing Bayesian inference under the hood. And this is very much the way that we use this kind of technology in trying to understand human behavior, where we say, this is the way that a system should behave if it's doing a good job of solving this problem. And it plus gives us a tool for being able to work backwards and reveal some of the assumptions that guide the system behavior. So hopefully I've convinced you that there's a meaningful connection between psychology and cognitive science, right? Sorry, psychology and computer science. Those of you who are computer scientists, I hope will enjoy talking to your colleagues for psychologists and vice versa.
Okay, there you are. Trouble, okay. Okay, and Ellie, it's yours.
Awesome. Thank you, Tom. Thanks for showing up when you're on your deathbed, on your COVID bed. Yeah, I think it's an awesome talk, and I really like this this topic and this line of thought. So I was writing down some thoughts and questions, and they're not really organized into a set of slides, but I'll just maybe start with the most pressing questions, and then if other people have questions, otherwise I'll go to other ones. So there's like an overarching question that I think I've been asked, and I don't remember how I answered, and now I kind of want to hear how you answer, which is like this issue of kind of, if you have language models that are good approximations of humans, like, do you get stuck when you use these kinds of methods? So I guess the story is like taking the Bayesian inference as an example. If we assume that humans are like, say, rational Bayesian agents, which we'll say there's other things going on, but let's just like assume for a second that. So the data that the language models are trained on were generated from that process. And the language models are doing a really good job approximating that data. And so it's like, by definition, then a similar Bayesian model is going to do a good job predicting what the language model does, but it's just kind of like almost a circular thing, right? Like it's like that nothing about what the language model is doing actually follows that process at all. It's just that the language model is doing a good job approximating the output of such a system. And I feel like maybe you could apply some logic to other kinds of things when you use psychological tests, right? It's like this was designed for humans as a test of the underlying mechanism of the humans. But now when you apply it to language models, we're basically getting like an artifact signature where it's like, since they're trained on human data to approximate humans, we're going to get a positive result, but it tells us, in the worst case, nothing about what's happening in the language model. And I was wondering your thoughts on that kind of line of criticism, or how you think about that.
Yeah, so I'd say 2 things, right? So one is, I think, I thought the ideas in your talk are sort of interestingly complementary to this, because your solution was go to the mechanisms and understand the mechanisms, right? And my solution is lift above the mechanisms and really focus on the sort of abstract problems. So the first thing I'd say is, I think that this approach is nonetheless valuable as an interpretability approach, where, what these models have done is learn to approximate some enormous probability distribution that we don't really understand, right? And so by building a smaller Bayesian model within a specific domain, you can pull out what it is that they've learned about the world in that enormous probability distribution, and then expressed it in the form of a much more sort of interpretable, understandable prior distribution that they're using for answering the questions that they're asking, right? So I think that's a valuable tool, is just sort of that interpretability tool. It's like, and that's part of the way that we use it for people, is just to say, what are people's inductive biases like? Oh, we can use this as a tool to then sort of pull something out and get a picture of what are the biases that are making people do what they do. And we have other papers where we've used this approach for doing things like looking at the priors that they have over causal relationships. So like, what sort of implicit assumptions do they make if you just ask them whether a causal relationship exists, or trying to estimate the strength of a causal relationship. The expectations they have about human decision making. So, if you ask them to make a decision or to predict what somebody will do when they're making a decision, what are their expectations about that? And so that gives us a tool that we can actually use to then make predictions about the way that they'll behave in other settings, where now they're making inferences about causal relationships. So they're making inferences from people's behavior.
Right.
The other thing that I would say is the other context where the Bayesian models are useful, and these basically correspond to the two examples that I gave at the start of the talk, right? So one is we can pull out a prior distribution. The other was, if we know what the sort of right Bayesian analysis is of a problem, and they end up doing something that's not that, then that's informative about things about the internal mechanisms that are sort of interfering with that approximation. And so the embers of autoregression examples were that, where we can say, we kind of know broadly what the prior distribution of these models is. It's whatever you learn from internet text. But if you're solving a deterministic problem, that prior distribution shouldn't be having an effect. And so if we can show that your prior distribution is having an effect on the answers you're producing when it shouldn't be, then that actually tells us something about, just like how we should be thinking about these systems, right? And if we're thinking about them and applying our sort of general intuitions about intelligence, which is that reasoning works in a certain kind of way and sort of has this logical structure and so on, but in fact, what they're doing is something that's much more fuzzy than that. That's a tool that we can use for diagnosing that.
One of my other questions I wrote down, did you test humans on those embers of autoregression things? Because I thought about like Gary's, and I was like, I bet you do see some of these effects, like counting. I'm sure people err on multiples of 10 with counting those exclamation points. I would probably mess up, and that seems likely, right?
Yeah, so I think, some of those are things that are much more straightforward for people than others, but what I would say is the kinds of effects that we're showing are not kinds of effects that are going to be unfamiliar to psychologists, right? So we're showing like frequency effects and practice effects, right? And those are the two very standard things that you want to appeal to when you're trying to understand human behavior.
Right. And so that's kind of where, like, in my original question, and I'm not trying to be critical, because I think this, like, I feel like it's that thing where you're like, oh, if the models show human-like biases, like, which I'm always like excited when I say that's like, oh, that's cool. It shows human-like biases. And then it's like, I get stuck because I'm like, was that a foregone conclusion? Like, of course it shows human-like biases. It was trained on human language data, right? Like, what, like, almost like, did we know that in the, like, if it shows human-like kind of content effects to human, like, of course it does. It was trained only on human data. Like, why would it have learned any other kind of biases? And so that's where I get stuck. And I wasn't sure if you had a thought for how to get out of that trap, right?
So I think that's a case where it's doing things that make sense to us as psychologists, but it's doing them in situations where people wouldn't do them. And so that's kind of why their errors are surprising, right? It's that, like, I think, it's like, maybe you can call it a system 1, system 2 thing, or whatever you want to call it, right? But it's like, it's doing something which should be an explicit reasoning task and reducing it to something which is much more like an associative inference task.
Yeah. Awesome. I see other hands, so I'll let somebody else take the floor. Awesome talk. Thank you so
much. Stephen, am I on, or?
Yes, you're the one with the hand.
Okay, great. I'm sorry to hear that you had COVID. I'm kind of feeling, after sitting through all this, that I have COVID, but that's another issue, I suppose. It's very interesting talk. And are you familiar with Larry Maloney's recent paper on probability judgments for GPT-4 and humans? I think it's in Nature.
Yeah, I haven't seen it. Yeah.
Nature something, and basically he set up, health tasks financial tasks, are you likely to have cancer, blah, 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 and then gave this to the chatbot and gave it to humans. And of course, their probabilities are correlated like 0.95. So sort of like we're showing in this context. So it's really quite amazing how little prior information, and I grant you there's probably a lot of prior information in the text, but a little prior information in the structure of this thing. And that somehow, and I believe you're right, that it implicitly garners some of that probability distribution from, the context that it's getting. Okay, but one concern I had was a perceptual kind of comparison. I did not understand why hex codes, which would at best give you 0 to 255 numbers, other than producing noise, and then multidimensional scale in a Euclidean sense will tend to produce, circles, just as a bias. Am I missing something?
So like, what do you mean? Are you missing something? So
Well, are the hex codes somehow known perceptually to GPT-4 as a color, or is
yeah.
it just a code?
No,
Really?
so it knows. So hex codes are used in internet text for referring to colors, and that's both in HTML, but you just see people on the internet saying, "Oh, I'm trying to figure out for a web page, should I be using this hex code or this hex code, or which of these colors is better for doing this." So we can find lots of instances of people talking about hex codes in the.
I see. So it could have inferred that
Mhm.
hex code 1 and hex code 2 are like red and orange, and therefore they're highly similar. That's sort of what you're getting.
Yeah, so it'll have like words like red and so on appearing with different associated hex codes. You can do some Googling of specific hex codes and
Oh,
find out.
I believe you. I've also seen a lot of examples where people have taken the original Shepherd results and run something through multimodal scaling, which often with a Euclidean metric will produce circles. So it's just
Yeah.
circles of almost numbers, letters, whatever you want.
So let me show you.
Color wheel.
So we have the similarity matrix, which you can use as a
Yeah,
model.
no, I'm sure you do. I'm not doubting that. I'm just, it's kind of shocking that it has perceptual sense about these things. And again, I guess probably out of context. I mean, there's hundreds of millions of contexts that it must in fact induce in this space. And certainly Anthropic has been showing some incredibly stunning pictures of the contextual space there. And yeah, that's it. Yeah.
Yeah. So this is the actual similarity matrix here.
No, I see it. I see it. It's shocking.
Yeah.
And so, but then really what you're showing is it's sort of human knowledge all the way down to the last turtle. As we go up to this thing, there's human knowledge everywhere. And sort of like what Ellie was saying, why are we surprised? Because that's what we've been giving it, right? So you're sort of confirming something that, and in an elegant way, but that should be true.
But I mean, I think the interesting thing here, and this is just on models that are trained on language, right, is that there is variation in how well this corresponds to people's representations. So, things like colors, it does a pretty good job on, but then like the timbre of musical instruments, it doesn't do a great job on. Mm-hmm. And I think you can understand that in the context of these models as being partly about a limitation of language and partly about just the frequency with which we talk about these things, right? And those things are, clearly correlated. But I feel like we just have much more linguistic specificity around color than we have around the timbre of musical instruments, right? You could say something is warm or something is sharp, or you have sort of a few metaphorical terms that you can use for this.
It just means that a lot of what Stephen's worried about in grounding is, in some sense, already, bootstrapped a bit in the text.
Yeah, but I think this also illustrates what the gap is, right? That to the extent that you're going to see grounding to the extent that there's some relational system which is well described by language, which can then be mapped onto the thing in the world effectively, right? And the language part of it is used enough that gets that thing into the representational system that the model is using. but there's going to be other cases where there's a big gap.
Yeah, I agree. One last comment, not pressing on the Bayesian part of this that was being brought up a minute ago. I seem to be disembodied, but I'll go on. Yes, obviously you can take any kind of cognitive function or cognitive capability and it produce some kind of Bayesian account of this. The question comes back is when you're doing this kind of reverse engineering, you need some assumption about these probability distributions to do some computation that is useful, right? I mean, it's not just enough kind of identifying the data and the hypothesis and the, all the little piece parts. It seems like a after the fact kind of analysis. I'm not sure what fundamentally comes out of it, other than you can do it, and there's lots of people who use Bayesian models, and I have nothing against that. I just not always sure what it adds.
Yeah. So, I mean, I think in this case, the interesting thing is, I think and the thing that's maybe sort of like unusual for somebody who's like used to building AI or machine learning systems is if, it used to be if you were a machine learning engineer, you would say, I'm going to build a system that solves this problem. And step one is I decide, should I make a Bayesian system or should I make a neural network system? Or maybe I'll do some other rule-based thing, right? You choose what flavor of modeling you're going to use, you build your system, and then you're done. And now we live in a different world where, these models are made with these neural networks and they build these giant neural network systems, but we don't really understand what those things are doing. And in particular, we don't understand what the assumptions are, the implicit assumptions that they're making about the world might be. And so I think the interesting opportunity of building cognitive models on top of a machine learning system is the thing that's sort of, novel and different and sort of something that's a interesting fact about the moment that we're in, where we can then say, okay, well, I made my big neural network, but what I really want to understand are what are the assumptions that this model is making when it's making a particular kind of prediction or it's when it's producing a particular kind of behavior. And for that purpose, actually building a simple Bayesian model on top of the behavior that's coming out of the neural network is something that can give you a different kind of insight, where it gives you a vocabulary for describing what the inductive bias of that system is in a way which is not expressed in terms of things like weights and attention heads and like all of the mechanisms.
I understand exactly.
Okay, just hold
I'm going to go away because Stephen wants me to stop talking.
Yes, stop talking. It's Julia.
Thanks for the great talk, and I liked your book, the algorithms. So it does seem that you're saying that when we find similar judgments to human sensory perceptions in the LLMs, they're partly grounded, and that those sensory perceptions are the ones that can be more easily encoded in language. And I was wondering, do you see any better performance in the LLMs in tasks that could leverage the areas that they seem to be better grounded in?
Yeah, that's a great question. So that's related to what we were trying to get at in the study that I presented with the moral reasoning, the value alignment study, because I'd say it's not necessarily grounded, right? It's sort of like pre-grounded in the sense that it has what I think Roger Shepard would call like a second order isomorphism, right? It's sort of like it has this representational structure that doesn't lie in correspondence with any kind of sensory experience or something in the world, but already has the structure that maybe corresponds to the structure that you end up with when you have that sensory experience, right? And so what we were interested in that value alignment study was if you have a system that has that kind of representation, and that representation is sort of structurally similar to the one that people have, then if you put the model in a situation where it's interacting with a human and the human is the one who's giving it the feedback, can it then more quickly acquire the function that the human being is teaching it? And so we've only looked at that in that setting, which was the moral reasoning setting, but that's sort of formally analogous to the question that you're asking, which is, like if you've already got something like the right sort of representation of these sense-related words, does that then put you in a situation where you're predisposed to be able to learn more quickly when you're performing a task that requires using that information? And the answer, based on our analysis in that moral reasoning case, is yes. That the degree of correspondence and representations is something that sort of is the degree to which you're primed to be able to learn those new relationships.
Yeah, I'm not interrupting anybody now. We're coming into the home stretch. Does anyone have anything to add?
Well, I can always keep talking, but it's just not.
You and
Like, I have a follow-up to Tom's discussion about modeling, and I agree with him that there's different modeling frameworks and they all have their own bias and so on. But in terms of mathematical statistics, there's a bias variance trade-off, and there's a whole field called model misspecification. So this is sort of the tension between learning something with a general function approximator where you're never going to accept the actual model. You're going to get close to it. There'll be some epsilon distance. Whereas you start with what you think is the model, and then you accept something. And the problem is, if that model was wrong, if you've misspecified it, then you're kind of stuck with the result. So you've raised the bias way too high. And so part of the difference between Bayesian rule-based neural networks and so on was this trade-off between that dimension. And that is in spades what's happening now.
Yep. No, I agree with that. Yep.
There we go. What a nice Friday afternoon.
Okay, well,
I'm done.
if everybody's run out of anything to say, I haven't. I want to thank Tom for the heroic effort that he made over here, and also Ellie for doing 3 sessions. No, yeah, 3 sessions plus your own today. Thanks very much. And
It was fun.
And I get off early so I can start uploading the videos so that everybody.
But Stephen, everyone should applaud you, who's ever on right now, for this amazing 2-week performance where the wheelbarrow hasn't come by and grabbed you and thrown you down and taken you away with a straitjacket. I'm just shocked you managed to do this, and it's impressive.
Who knows tonight? Who knows what's going to happen?